Assalamualaikum and greetings everyone. Today's topic is on a piecewise surface integral. Okay, now let's look at what is a piecewise surface. A piecewise surface is several surfaces joined at some of their boundaries. So to evaluate a piecewise surface integral, we calculate surface integral for each surface involved and then add them up. Okay, so this technique applies to both surface integral of a scalar field and also surface integral of a vector field. As an example, I'm going to show you surface integral of a vector field. Okay, so here we are asked to find flux or flow of a vector field given as this, spreading through the piecewise surfaces sigma, involving three surfaces, x0, z0, and x equals 1, that lies in the first octant in between y0, y3, and the top by z equals 3. So here we have x0 is a vertical plane, z0 is a horizontal plane, and x equals 1 is another vertical plane. The three surfaces, the three planes lie in the first octant, but it doesn't go to the left forever because we have y equals 0. And then it doesn't go to the right forever because we have this y equals 3. And it doesn't go up forever because we have, they stop at z equals 3. Okay, so let's look at our surfaces. All right, now let's sketch x equals 0. So x equals 0 is a vertical plane that lies on the yz plane. But it doesn't go up forever because we have the boundary z equals 3. So let's say that's x equals 3. And sorry, z equals 3. And it doesn't go to the right forever because we have y equals 3. So let's say that's a 3. This is a 3. So this is our first surface. Let's call this surface sigma 1. Okay. And then we have another surface, another vertical plane, which is x equals 1. So again, it doesn't go up forever because we have z equals 3, and it doesn't go to the right forever because we have y equals 3 here, and then we have y equals 0 as well, so it doesn't go to the left. Let's sketch that. 1 2 3 4 1 2 3 4. So we have a vertical plane, another vertical plane. 3 4 1 2 3 4. Okay, so let's call this sigma 2. Okay, and then we have another plane, z equals 0, which is really a horizontal plane. So z equals 0 is this plane here. Okay, let's call this sigma 3. Okay. All right, so to evaluate flux, as you know, flux is f dot unit number vector ds integrate over surface sigma. But since our sigma is a piecewise surfaces, so we need to evaluate the surface integral over sigma 1 plus surface integral over sigma 2 plus surface integral over sigma 1. Okay. All right, now let's evaluate piecewise surface integral over sigma 1 first. Okay, so our surface sigma 1 is this one. Okay, it is vertical and the shape is a square. Okay, I'm gonna use the next page. Okay, now let's say we want to look at surface sigma 1 where it is equal to where x is equal to 0. As you can see, the surface is facing the negative x-axis. Okay, so the normal vector would be pointing to the back. Okay, so since it is facing the negative x-axis, we need to check for the x component, and the x component should be -1. Okay, since it is facing the negative x-axis, so we want our x component to be -1. All right. Okay, now we know that the normal vector to the plane is really negative 1i plus 0j plus 0k, but I'm going to show you the technique that we used in the previous example. So first of all, rewrite the surface sigma 1 as a function of x, y, and z. So this is only just x equals 0. And find the gradient of phi. That would be our normal vector, one of the normal vectors, and then we have to pick which normal vector to choose. Okay, so here differentiate phi with respect to x, we get a 1. With respect to y, we get a 0. With respect to z, we get a 0. But remember, we have to check for the x component. We want our x component to be negative 1. But here we can see that it is positive 1. So the normal vector would be negative del phi, which is equal to negative 1i plus 0j plus 0k. Okay, next we need to evaluate f dot n. Okay, f is xi plus yj plus 3xk. So we have x, 2y, 3x. Dot that with the normal vector to the surface sigma 1. So from here we get negative x plus 0, which is negative x. Okay, now we want to find the flux of f when it's spread along sigma 1, surface sigma 1. So what we do is we project this onto a region R. Since our surface is given as x as a function of y and z, but in this case it's just equal to 0. So we're going to project this onto the yz plane. And unit normal vector ds will be replaced by normal vector dA. And our region R on the xy plane is just a square. On the yz plane, it's a square. Okay, so it's blue. So it's just 3 times 3. Okay, so y is from 0 to 3. Z is also from 0 to 3. Okay, so we already calculated f dot n, which is really negative x. So now we're going to evaluate this. We're going to integrate this over region R, which is on the yz plane. Okay, so that would be dz dy or dy dx. It doesn't matter because it's a square. You can do it either way. So y is from 0 to 3. Z is also from 0 to 3. And then we have negative x here. Now the integration is with respect to z and y. So that x there must be replaced with our surface. Okay, but our surface is x equals 0. Which means that we're gonna integrate 0 over the region R, 0 to 3, 0 to 3. What we get is a constant, and then that same constant minus upper and lower limit, then what we get is a 0. So the flux of a surface sigma 1 is 0. Okay, now we're gonna evaluate flux of f over surface sigma 2. So here I'm using x equals 0 as sigma 1. Okay, for sigma 2 we have x equals 1, so I'm going to call this sigma 2. So now we're going to look at the flux over surface sigma 1. Sorry, sigma 2. Okay, for over surface sigma 2 we have x is equal to 1. Okay, now from the diagram we can see that x is the surface sigma 2 is facing the positive x-axis. So if it's positive x-axis, we check. We want our x component to be positive 1. Okay, so here we have our surface sigma 1. Okay, hang on, let me erase surface sigma 1 first, and then look at sigma 2. So this is our, oopsie, oh dear. Okay, so this is our surface sigma 2. Okay, it is facing the positive x-axis. So we want our I component to be positive. So this is the normal vector. It's facing the positive x-axis, meaning that we want our x component to be positive. In fact, we want it to be positive 1. Okay. All right. Now, again, rewrite the equation for the surface as p. So that would be x minus 1 equals 0. Get the gradient of phi, that would be your normal vector, or negative del phi would be your normal vector. So here we have 1, 0, 0. and check for the x component. It is already positive 1, just like what we want. Okay, so this is the normal vector. Okay, now dot f and n. F is equal to x to y 3x, x to y 3x, and the normal vector is 1, 0, 0. Dot the two vectors, we get x plus 0, which is x. Okay, so now we can evaluate the flux. F dot n, f dot unit normal vector n, integrate over surface sigma. So what we do is we project our surface sigma onto region R, and then dot normal vector ds will be replaced by normal vector dA. Since our surface is given as x as a function of y and z, so we're going to project this onto the yz plane. Okay, so we already calculated f dot n. This is equal to x over region R, which is on the yz plane. And when we project our surface sigma 2 onto the xy plane, we got exactly surface sigma 1, which is a square. So our region would be the same as this. Okay, when we project our surface sigma 2 onto the yz plane. So we need to evaluate this by integrating with respect to y first or z first. It doesn't matter because we have a square. So let's say dz and then dy. So y is from 0 to 3 and z is also from 0 to 3. And now we need to change this x here. Okay, with our surface. Remember, the surface of sigma 2 is x equals 1. So we end up with calculating integrating dz dy 0 to 3, 0 to 3, which is really the area of your region. And you can see that the area is area of a square, which is 3 times 3, which is 9. Okay, but we're going to use double integral, of course. 0 to 3, 0 to 3, oops, sorry. Integrate with respect to z, we get z 0 to 3 dy, so we get 3 dy 0 to 3, so we have 3 y 0 to 3, so this is 3 times 3, which is a 9. Okay, so that is the flux of a surface sigma 2. Okay, now we're gonna proceed with, so we already calculated this one. So the first one is 0. Oopsie. The first one is 0. The second one is 9. Okay, now we're gonna evaluate over, oh, that's not sigma 1. That should be sigma 3. Okay, now we're gonna evaluate the flux of a surface sigma 3. So what's left is z equals 0. Okay, so now let's look at our surface sigma 3. Okay, let's see here. Our surface now is horizontal plane. Okay, and it is facing the negative z axis. So our normal vector would be pointing, oopsie, sorry about that, will be pointing downwards. Okay, downwards, which means that we are looking for z component to be -1, okay, because it's facing the negative z axis. I'm going to show you in detail. All right, so on surface sigma 3, we have z equals 0. Since the surface is facing the negative z axis, we want our k component to be negative. In fact, we want it to be -1. Okay, now rewriting the surface as p, it's going to be z equals 0. So the gradient of phi is 0, 0, 1. But we want our z component to be -1, which means that the normal vector would be negative del phi, which is 0, 0, -1. Okay, now let's evaluate f dot n. F is xi plus 2yj plus 3xk, if I'm not mistaken. Yep. And the normal vector to our surface sigma is 0i, 0j, minus 1k. So from we get 0, 0, minus 3x. Okay, so now to evaluate the flux of F, over surface sigma 3 is f dot unit normal vector n ds. But now we're going to project this onto a region R. And here we have z is equal to a function of x and y, but in this case it's just 0. So it's going to be, we're going to project this onto the xy plane. And dot unit normal vector will be replaced by normal vector dA. All right, and we already calculated this. It's equal to negative 3x. And now looking at your surface sigma 3, then we can see that when we project this, well, it is already on the xy plane. When we project this onto the xy plane, we get a rectangle where x is from 0 to 1 and y is from 0 to 3. So that would be the projection of your sigma 3 onto the xy plane. In fact, it is already on the xy plane. Okay, so here in this case, you can evaluate, you can integrate this with respect to y first and then x, or x first and then y. So y is from 0 to 3 and x is from 0 to 1. Okay, here you don't have to replace x with anything because the integration is with respect to y and x. But if you have z in it, then you have to replace it with 0. Okay, integrate negative 3x with respect to y, we get negative 3xy, 0, 3 here, so we get negative 9x. Now we're going to integrate that with respect to x. So we get negative 9x squared over 2. Replace x with upper and lower limit, we get, excuse me, negative 9 over 2. Okay, so now we're going to add everything together. So on the first surface sigma 1, we get a 0. On the second surface sigma 2, we get a 9. And then on surface sigma 3, we get negative 9 over 2. So add them together, we get this is equal to 9 over 2. So that's how you evaluate piecewise surface integral. Evaluate on each surfaces and then add them together. Thank you.